So
Can you share, or I have to give you?
no, I think it's fine. Just let me change the video camera.
Ah.
But also, I think I have to activate the. Okay. Okay, so one moment. Okay. And now it should be possible. So, are you seeing my face?
Yeah.
Yes.
Yes. And now you see, okay. Is it fine? Do you see it well, or it's?
Yes.
Yes. Is it this solution fine? Because otherwise I can also try to use the iPad as Sandra, but I'm much worse than Sandra at using it. So I'm not sure that it's gonna be better.
But for me, it looks perfect.
I can also usually read everything.
Okay, and okay, so let me recap from the last time, because I did, I mean, it was not very polished, the proof I was giving of the. So let me just recap the main points. So first point is, well, let's do it, forcing theorem. Well, I use, the point is, I'm most of the time I'm working in Morse-Kelley, and sometimes I also need to work in the Gödel-Bernays. So let me just outline the difference. So the difference between, so idea in both cases, idea for Gödel-Bernays and Morse-Kelley, we work in V delta or V delta plus 1 for delta inaccessible. So the universe is the cutoff of the standard set theory universe at an inaccessible. Okay, and the standard model of GB is V delta epsilon and then A for A, which is the subset of V delta. So the difference and the standard model of MK is V delta plus 1 epsilon V delta. So the difference between those two models is that in the GB model, you look at classes as predicates. Okay, while in the MK model, you look at classes as elements of top rank. And the difference between these two first order structure is that here you can quantify over classes, while here you cannot. The quantification range just over sets, but you can use classes as predicates. Okay.
Bernays Gödel, is it that should be conservative extension?
Yes, yes, it is.
Oh, okay.
But and I mean, for the purpose of my talk, I'm never going to need to use quantifiers with ranges over proper classes. So I could even work in Gödel-Bernays, it would be okay. But I mean, I don't want to put a limitation on the expressive power, and I don't think it's gonna change much in what I say. So it's simpler to work in MK. Is it fine? I move on.
Yes.
Okay, and now forcing theorem. In both cases, I state it because I need it in, I use it in both cases actually. Forcing theorem. Assume P is a class predicate in the model of GB, such that V models P is poset. Let G be V generic for P, then VG models P of tau 1, tau n, if and only if there exists a P belonging to P such that V models, P belonging to G, V models, and here is tau 1 G, tau n G, such that P forces P T of tau 1, tau n. Okay. So writing this way in Morse scale, it makes perfect sense. If I want to say it polished in Gödel-Bernays, well, this P is not really an object; it's a predicate. So I would have to say the axiom stating that this predicate is the extension of a partial order, and then I would have to be slightly okay. On the other hand, is tau 1, tau n are elements of V P, so are P names in V, so are sets. Okay. And well, this is Gödel-Bernays version, and the Morse-Kelley version is let P belong to the classes such that C epsilon V models P is a poset. Let G be C generic for P, then CG epsilon VG models P of tau 1 G, tau n G, if there exists a P belonging to P such that T epsilon V models P forces in P of tau 1, tau n. Okay, is this fine? Is this clear? Both these theorems can be proved in both theories.
Wait a minute, like literally 30 seconds.
So I move on. Is the statement and the content of both theorem clear?
Yes.
Okay. So now let's consider the other lecture. We considered call omega less than order. Well, this is clearly a definable class in ZFC, in a model of ZFC. Okay, so we are in the setup. So we are in this setup. This is an element of, well, actually, I mean, here you can decide how many predicates you want to add. Here you can just add the predicates for a formula with parameters in V, and call omega less than delta will appear among these predicates. Call omega less than odd will appear among these predicates. Okay. And now we observed that well, actually one can prove lemma let V epsilon A belongs to C, so the model GB, or V delta plus C epsilon V models MK. Then, so let us call this structure A. Then A models P is pretime, which means i.e. P preserves regularity of order. actually you can prove more. In both cases, you can prove that A models P is less than order CC. So the anti-chains in P are set size. Okay. And furthermore, we have that if G is, well, actually, in this case, there's no ambiguity because being V generic, well, it's the same as being C generic. Because the anti-chains are small, so they are set. And in this case, so if you are meeting all the anti-chains, this is detected at the level of V, not at the level of C. Okay. Because of this, if G is V generic, we have that VG models ORD is the first uncountable cardinal. And all sets are countable. So it
Sorry,
is in essence.
what is P on this slide? Like P is like is P some previously specified forcing or
What?
is P some previously specified forcing or
Yes, call omega less than order.
okay,
sorry.
okay.
Okay, and here I put VG. Well, maybe a better notation would be AG, which has to be declinated according to whether we choose this stuff or this stuff. Okay. So what happens is the effect of this forcing, of this class forcing, is to make every set countable while preserving the regularity of order. So in essence, when you force with this forcing, with this class forcing, you are making the universe looks like H omega 1. Okay. So I move on. Is it fine for everybody?
Yeah.
Okay. And then last time I proved, well, more or less proved lemma. Assume C epsilon V models MK and G is V generic for call omega less than ORD, and delta is inaccessible and such that V delta epsilon is an elementary substructure of V epsilon. Okay. Then letting H equal G intersection V delta, H is call omega less than delta generic. Well, is V generic for call omega less than delta. And here you can choose V or V delta because call omega less than delta is less than delta CC. So all the anti-chains are actually living in V delta. H omega 1 of VH is equal to V delta H is elementary in VG. Okay. And the proof split it in several parts. Some of them were more or less clear and some were not. So let me recap the one that were not. So, well, I recap everything because actually it will be faster. Okay, so what is the, let me take my notes, which so the idea is the following, which is actually, well, actually we can do it like this also, H omega 1 of CG, okay, because for C it makes sense. Okay. So this equality, H omega 1 of VH is equal to V delta H follows from forcing theorem for GB applied in V delta epsilon epsilon, well, I mean, it follows from many possibilities. So one possibility is this, V delta epsilon A is a subset of V delta relative to call omega less than order. Sorry, yes, call omega less than order is computed in this structure because call omega
Sorry,
less
just
than delta.
where's it applied?
Huh?
Where is it applied? The last sentence of the. Okay, yes.
Call omega less than delta is a complete subforcing of call omega less than order. And also we have call omega less than delta is less than delta CC. So all names for elements of H omega 1 V H are in V delta. All P names, well, or call omega less than delta. Okay. So this equality follows by whichever version of the forcing theorem you like. You can apply the forcing theorem. Well, I mean, whichever consideration about this forcing you make in either of V delta or V delta plus 1, you use the fact that this forcing is less than delta CC, so that all names for elements of H omega 1 have rank less than delta, and you get this equality. Okay, so this equality is fine. Now this part. So this part required the following observation, which I skipped, and unfortunately I forgot to put it also in the paper. So it's not present even in the paper if one looks there, which is the following. For tau 1, tau n belonging to V delta, and P belonging to call omega less than order, we have that V or V delta or V or C, I mean, it doesn't really matter. You can work either in the setup of Gödel-Bernays or in the one of Morse-Kelley, and it's the same. So let's use it, epsilon A belongs to C. Models P forces P of tau 1, tau n in call omega less than order, if and only if V delta epsilon A subset of, well, in this case, yes, models P intersection V delta forces call omega. Well, actually, no. Let me leave it like this, so it's no problem. A belonging to C. I mean, it's the same because of elementarity, and the proof will use it. P of tau 1, tau 1. Call omega less than order. Okay. So what is this observation saying? It's saying if I have a condition which forces that the formula holds true with parameters of small rank, they belong to V delta, Well, actually, I just need the piece of the condition which lives in V delta to witness this. I don't have to take the piece of the condition which is outside of V delta. Okay. And I mean, for this specific forcing, you can use two proofs. One is appealing to the fact that this forcing is homogeneous and is more general. It works. I mean, you just need that you cut off your P at any alpha which is of rank bigger than tau 1 tau n, than the rank of tau 1 tau n. But we won't use this proof. We'll use another proof which is using the fact that V delta is elementary in V. So because this other proof is going to work also in the more general setup I'm going to use with other class forcings. So is this fine, the claim, the statement?
Yeah,
Yes.
for me.
Okay. So let me prove this observation because this one I didn't say the last time and it's important to run the argument smoothly. So how does this work? Well, assume not. Then you find P force. I mean, in one direction, it's clear. If P belongs to V delta, there's nothing to prove. So then there is P, which forces P of tau 1 tau n, such that P intersection V delta does not force P of tau 1 tau n. Okay. And here it's important that I'm using col omega less than ORD. And here is col omega less than ORD. Okay. Well, but now we have that V delta epsilon is elementary in V epsilon, and this stuff belongs to V delta, which implies that V delta epsilon models that P intersection V delta does not force in col omega less than delta P of tau 1 tau n. Okay, then by the forcing theorem, let me be careful because I want to number correctly the stuff. So 1, 2, 3. 4, 5. Okay. There is R belonging to V delta, R less or equal P intersection V delta, R forces, well, V delta epsilon models that R forces not P of tau 1 tau n. Well, but now we have that R and union P belongs to col omega less than ORD. Why? Well, because their common root is P intersection V delta. I mean, I mean, R, what is R? R is a function that goes from omega cross delta to delta, while P is a function that goes from omega cross ORD to ORD. And we have that well, we have that P restriction to V delta, which is equal to P intersection V delta, is a subset of R. So the two conditions are clearly compatible in col omega less than ORD. And by elementarity, we get that V epsilon models that R forces in col omega less than ORD not P of tau 1 tau n. And here we reach the contradiction. Okay, because I have two compatible conditions which are forcing contradictory statements. Okay, is it fine?
Yes, yeah.
Okay. And now we can complete the proof, and I guess this time it should be without problems for everybody. So let G be V generic for call omega less than order, and H be equal to G intersection V delta, then H omega 1 of VH models P of tau 1, then for tau 1, tau n belonging to V delta intersection V call omega less than order. Okay, we have that VH, which is actually equal. If one thinks a bit about it, it's just the same as V call omega less than delta intersection V delta. We have that H omega 1 models P of tau 1, tau n G, H, if and only if VH models P of tau 1 H, tau n H. Here I'm using the fact that we have this equality. If and only if V delta H, V delta models, there exists P, if and only if there exists a P belonging to H such that P forces such that V delta epsilon force models that P forces in call omega less than delta P of tau 1 tau n. And here clearly I have this direction, which gives there exists a P belonging to G such that V delta epsilon models, here I can change using elementarity. V epsilon models P forces in call omega less than order P of tau 1 tau n, which gives me that VG models P of tau 1 G tau n G, but clearly tau 1 H is equal to tau 1 G for, well, actually tau J for J equal 1 n, because I mean this in order to evaluate these names I just need the condition which lives in V delta of the generic. So I'm fine. I mean one direction is okay, so I have this other implication. Well, and this other implication is given by the observation I gave before. If I find the P in G which forces this stuff, actually I just need the piece of P which is in V delta to force this stuff. So I can get this back using this observation. Okay. Is this proof clear, or should I expand on some pieces of it?
Could you give like 2-sentence overview because I'm kind of globally in the last part.
What?
Could you just not maybe expand, but just summarize what happened in the last, let's say, two sentences?
So I'm doing, so what happens here, I start from this direction. So one direction is fine. If I start from here, I end up having my formula through here. So now I go backward. So I go backward from this, I get this by the forcing theorem. Well, and now the problem is that I have my P which belongs to G, which may not be, I need the P belonging to H in order then to continue. But I can change from G to H using the observation 2, which says that that if I have tau 1, tau n, which, sorry. So if I have tau 1, tau n of small rank, they belong to V delta, and I have a condition P which forces P of tau 1, tau n in col omega less than order, it is actually enough to take P intersection V delta to force P of tau 1, tau n in col omega less than order. So you see from this fact, I can move this fact because, well, actually, to be precise, we get that P intersection V delta.
So like, so everything you're using is simply that call omega less than art intersected with V delta is isomorphic to essentially, is isomorphic to call omega less than delta, right?
It's actually col omega less than delta. It's
Right.
not isomorphic. It's really the same. So maybe it's better that I spell out the definition, which I wrote of what is for me col omega less than delta or col omega less than order. So there are, so P belongs to col omega less than delta, which means that P goes from omega cross delta into delta, is finite, and P of n alpha belongs to alpha for all n alpha in the domain of P. So this is the standard forcing to collapse delta to become the successor of omega. Maybe you find some different definition in the books, but more or less this is one standard definition of this forcing. Is this okay? Should I go back to something? I mean, this remark you made make me suspicious that I have been hiding too much. I mean, supposing too much for known.
It's fine with me.
Okay, so I move on. I mean, I'm ready to discuss, but I need the inputs if you want me to discuss. Otherwise, I move on.
Okay.
For me, it's fine if you move on.
Huh?
I'm fine if you move on.
Okay. Okay. So what is the corollary? Assume T epsilon V models MK plus ord is malo. Then for any T poset set sized, sorry, maybe it's better to change letters so you're not confused. So poset which is set sized, so it is a set. There exists R less or equal Q, also set sized, such that R forces projective resurrection, which, let me recall definition, PR holds in C epsilon V the model of MK plus Ord is malo.
But here, if you say R less than or equal to Q, do you just mean subset?
I will expand. Let me recall projective resurrection, and then I will say what is this. Such that and H omega 1 is elementary in VG. Sorry, yes, in VG. If G is V or C generic, I mean it's irrelevant. G is C generic for call omega less than Ord. So this axiom is saying the H omega 1 of the ground model behaves like the H omega 1 of the Solovay model. Okay. And what is this definition for PQ posets? P is less or equal than Q if whenever G is V generic for Q, there exists H belonging to VG, V generic for P. So R is less or equal Q means if I force with R, I'm adding also a generic for Q.
Is this equivalent to saying that Boolean algebra for R is complete subalgebra of the algebra for
Yeah, I
Q?
will come to that soon.
Okay.
For the moment, let me stick to the forcing terminology.
So why do you call it projective resurrection?
I will come to that. I anticipated last time. So projective resurrection because of this fact. Assume V models MK plus Ord is malo plus well PR. Then for every Q set sized poset, there exists a P less or equal Q set sized such that H omega 1 of V and H V generic for P such that H omega 1 of V is elementary in H omega 1 of VH. So what happens is that I start with the theory of H omega 1 in V, then I destroy it using some forcing Q. Maybe I'm adding a projective well ordering of the reals, and then I force with call omega less than gamma for gamma large enough, so to absorb Q, and I restore that there is no projective well ordering of the reals. Okay, so it's this. And why this is the case, I proved this fact last time. Proof given Q as above, find delta bigger than the size of Q, such that V delta epsilon is elementary in V epsilon, delta inaccessible. Pick H V generic for call omega less than delta, and G V generic for call omega less than Ord with H equal G intersection V delta. And then we have the following situation: H omega 1 of V is elementary in VG. And then here we have the substructure relation with H omega 1 of VH. And here we have the elementary substructure relation, because this forcing, I mean, we have just proved that this forcing col omega less than delta is establishing projective resurrection for this stuff. Okay, so here we have this structure is elementary in this one. This one is elementary in this one. This one is a substructure of this one. So here this substructure relation extends to elementary substructure relation by the Tarski-Vogt criterion. If you take an existential formula with witnesses here, which is true here, it is true here, and then it reflects here. Okay, is it fine?
Yes, thank you.
Okay. So you see the large cardinal assumption of this result are very weak. They are ordis malo. Essentially, if you are in a model, you can prove it the consistency of this projective resurrection in V equals L. You cut off the, well, V equals L plus there is a malo cardinal. You cut off the universe at L delta plus 1, where delta is malo. You make all your argument in L delta plus 1, and everything is fine. Okay, and let's compare it to definition, projective absoluteness. Which, well, I don't know if PA is a good name for it, because which states for any set size posted P, if H is V generic for P, we have that H omega 1 is elementary in H omega 1 of VH. Okay, so clearly, I mean, so well, maybe no, let me phrase it slightly different. I mean, more or less it's the same, but maybe this is slightly weaker than what I want, what I need in order for the argument to run smoothly. So let me phrase it this way. In MK plus nothing. In MK, for any P set size, we have that and G V generic for call omega less than order. If H belonging to VG is V generic for P, then H omega 1 of VH is elementary in VG. Okay, so projective absoluteness is a very strong form of projective resurrection. Projective resurrection says, okay, I start with my model of set theory, where I know that forcing with col omega less than order, I get the same theory of H omega 1. Then I change this theory, for example, adding a projective well order of the reals. then I can re-kill this theory and get back to a theory where the theory of H omega 1 is still elementary in the theory of H omega 1 as given by col omega less than order. Okay, while projective absoluteness says, okay, you are already, whatever forcing you take, you cannot change the fact that the theory of H omega 1 is really given by the theory, the Solovay model obtained by col omega less than order. Okay, and fact PA plus, sorry, MK plus ord is malo models that PA implies PR. Well, this is trivial. Okay. And the other fact is MK plus ord is Woodin models PA. Or maybe do I need, yes, I think it's fine. I think it's fine. I think it's enough for all this wooden for so all forcings of size. I mean, yes, the proof in Larson's book works with it. I mean, all forcings which belongs to, supposing that that we are working at the level of some delta which is wooden. We know that if you take a forcing of size less than delta, you cannot change the theory of H omega 1 using this forcing. Okay. So is this fine so far?
I think so.
Okay, so you see this passage to class forcing allows to give some, let's say, some variation of the standard formulation of generic absoluteness for second order arithmetic, which allow, for example, for this consistency of projective resurrection, which is much weaker in consistency strength than projective absoluteness, I think. I think you cannot get with much less than wood into projective absoluteness, but I mean, this is already saying that the canonical theory of H omega 1 is the one given by the Solovay model. Okay, and the point is that this is what can be generalized to bounded forcing axioms. What is the idea? Well, the idea is how do you get to a model of bounded forcing axiom? You try to make true all sigma 1 sentences with parameters in H omega 1 that you can. And along the way, maybe you are collapsing H omega 1, so you have to make true more sentences with more parameters. But at a certain point, you may catch up. And for example, if you do this process smartly enough and for length reflecting cardinal, you end up with a model of bounded forcing axiom. So if you do this in the model of MK and you say order is, let's say, probably, I guess, to get the consistency, I guess, malo. Actually, what happens is that all this malo is sufficient. Then you may expect that that when you force, I mean, when you do an iteration of length order, which is the standard iteration that you use to try to force bounded forcing axiom, then the generic extension that you get is actually making the. So let me write, because so suppose P alpha less than ord is an iteration of proper forcing chosen wisely enough to make true more and more sigma 1 sentences in set size parameters. Okay, then let P equal the limit over order of this P alpha. Well, let's say P alpha dot Q alpha. And the iteration theorems. So you might think that that this order is actually a delta for inaccessible delta. The iteration theorems tells that P is proper. Okay. Well, here you have to put quotes because P is a proper class now, but in particular, P preserves omega 1 of V, and along the way you can imagine that the process has collapsed every ordinal to become of size omega 1 and makes order become omega 1 plus. Okay, so it makes it omega 2. Okay, and now the idea is that if this iteration has been chosen so that the iterants are generic enough, chosen generically enough, then at the end what you end up is with the theory of H omega 2, which is making true bounded proper forcing axiom. If H is V generic for P, VH should model BPFA. Okay, well, it's not clear exactly what BPFA looks like because now you don't have much more room to force a game, but I will spell out. Okay, and also if your iteration is of length order, you may suppose that at many inaccessible stage, if you cut off this iteration at that inaccessible stage, you are getting, let's say, for many delta, can expect that V delta H intersection V delta should be H omega 2 of V of P delta, well, of P alpha, Q alpha, alpha less than delta, and should be elementary in VH. Okay, and this stuff now should be a model. I mean, so you should expect that when you're forcing with this P delta here, really you're getting to an intermediate stage where this intermediate extension is modeling BPFA. Okay, so this is the idea, and now we have to make it a better definition than this vague phrasing. So is this fine? Is this
Yes.
yeah, okay. So definition. Okay, so the first point is what is the class forcing that we are going to use? So we are going to use the forcing made of forcings. So for this, it's better that I make the tour. So given B, well, given I, no, so fact. Let B, C be complete Boolean algebras. The following are equivalent. 1, there exists I from B to C complete homomorphism, possibly not injective. This is important. And 2 is that C plus is less or equal than B plus. That means whenever you add a generic for C, you are adding a generic for B. So let me prove from 1 to 2. So why I want to use this fact? Because what I'm going to do now is I'm going to I want to rephrase many facts that we are used to phrase them in the forcing terminology. I want to phrase them as properties of Boolean algebras, algebraic properties of Boolean algebras. So for example, this is in the forcing terminology. This is an algebraic property.
Okay, I have a question. Assume that we are in the case 1. So is B then forcing equivalent to the image of I?
No. No, in general, not. What happens is B splits in 2 pieces. One, which is a complete subalgebra of C, and the other piece, which may do some completely different stuff as a forcing notion.
Okay. So, but wait, well, okay. So, but if I give you now generic for C,
Mm-hmm.
you can pull it back to B.
Yes, using I.
And it will be generic.
Yes. Yes. But the problem is, for example, there could be a condition in B.
No, but
Which
this makes no sense because the pullback of generic by I means, I mean, depends only on the image of I.
Yes, but if I is not injective, there could be something which is mapped to 0 by I, and this something is never going in to be in the generic for C.
Oh, I see. Okay.
So let's see that 1 implies 2. If H is V generic for C, and I minus 1 H equal G is V generic for B, because if A contained in B is a maximal antichain, I of A is maximal in C, so there exists a B belonging to A such that I of B belongs to G, which implies that B belongs to B belongs to H, which implies that B belongs to G. Okay? And 2 implies 1. Let G point equal C check C, C in C, be canonical, C name for, well, let me put here a subscript for the V generic filter for C. Okay, and now we want to define the embedding, the complete embedding, and define let let G let G be C generic, well, V generic for C, well, let me do it like this, and let H point belonging to VC be such that H point is V generic for B check, C is 1. Okay, so this follows from this condition is saying that I have this C name for a generic filter for B. Okay, and now my map is IH point, which goes from B to C. What does it do? It takes B and it sends it to the Boolean value that B check belongs to H dot C. And it's clear that this is a homomorphism. And actually, it's not much work to check that it's a complete homomorphism. Okay. Note.
Oh,
that-
okay. Can I ask? Sorry, I will wait for the note.
Yes. Note that IH need not be surjective. Sorry, need not be injective. As B check belongs to H point equal 0 C for some B in B is no problem.
Okay, so let's say in 2, now you
Mhm.
replace, instead of this condition, you have the following condition. Every generic for B can be extended for generic for C. Do you then
Yes,
get?
then you get injective.
Okay.
Actually, it's better the other way around. Every well, I would say rather like this. Every condition in B, for every condition in B, there's a C generic, which such that when you, well, I would say it like this. Whenever B belongs to B, there exists H, B generic for C, well, HB, B generic for C, such that in VHB, there exists G belonging to VHB, B generic for B with B belonging to G. But it's more or less what you're saying.
Okay.
While this is saying whenever G is V generic for C, in VG exists H V generic for B. Okay, but it could be that you cannot find whichever generic for C you choose, you cannot find a generic which has a specific condition of B inside. In which case this homomorphism is not injective. Okay, can I move on?
Yes.
Okay, and now let me definition given let gamma be a definable class forcing. Well, a definable class in of Boolean algebras well, actually of forcings, it's better, of posets, closed under two steps iteration. What does it mean? I.e., there exists, well, there is P gamma of X formula such that gamma is equal to the B such that V epsilon models P gamma of X. And if B belongs to gamma and C point, well, P gamma of C point B is equal to 1 B, then B star C point belongs to gamma. So B epsilon models. Okay, so I'm phrasing this in the language of in the forcing language for complete Boolean algebra. So this is being closed under two-step iteration. Or let's use it posets, so it's more clear what happens. P Q, and here it's P star Q. So everybody knows what P star Q point is. Maybe B star dot C for B and C complete Boolean algebra is less clear. So is it fine? There's and then we say that P is less or equal gamma of Q if and only if the well, no, let me say I from for B C complete Boolean algebra such that B plus C plus belongs to gamma. We say that I from B to C is gamma correct if the Boolean value of C check mod I of G point B sorry, belongs to gamma. Well, let me rewrite it properly. If the Boolean value of P gamma of C check mod I of G point B is equal to 1B. Okay, and this translated in the forcing terminology, this means whenever G is V generic for B, we have that C mod IG is Boolean algebra in VG, and seen as the forcing, we have VG epsilon models P gamma of C mod IG. Is this right up clear? What is this? Well, we are in the setup of Boolean algebras. So G is the filter, and we can make the quotient of a Boolean algebra by well, I of G generates a filter, or you can take the dual ideal and you can make the quotient ring. Okay, so by this, so C mod IG is the quotient ring of C modulo J, where J is the ideal dual to the filter on C given by generated by IG. So the upward closure of IG. Okay. Is this okay? Am I rushing too much, assuming stuff about Boolean algebras? So it's convenient at times to look at Boolean algebras as Boolean rings so that we can quote stuff about about rings without problem.
I think it's fine.
It's
Guys,
fine?
can you also respond? It's fine. It's fine. I think.
Okay, so I move on.
Do you still here? So here for I, you still assume that it can be, I mean, non-injective.
Yes, non-injective.
It's
But
okay.
if it is a complete homomorphism. So, but I'm assuming it is a complete homomorphism. So this is always an implicit assumption, completeness. Injectivity, no.
Okay, but okay, so let's say now you have this. If you can take image of B via I in C, so now you have this quotient algebra C over I GB. So
Yes.
you will have that C is actually equal or isomorphic or whatever to I to the I
yes,
of B
you will have
star.
that,
Okay.
yes.
But what happens on the B side of the equation?
I will tell you. So
Okay.
the theorem, which I don't prove, but if you want, I have written up notes on that, so I can give you reference for this. The following. So theorem or lemma, let I from B to C be a complete Hom of CBAs. Then we have that then B plus star C hat. What is the, so it's this C check mod I G dot B.
Just a comment.
Plus,
He has notation for this thing. He writes C two dots I of B.
Who has this notation?
Yeah.
Okay. Well,
Like
I use this notation. Is it unreadable or it's okay?
No. I mean, it's okay. It's just a little bit cumbersome, but it's okay.
Okay. Is this is a poset because I'm using here the Kuhnen's definition. So if I take the Boolean completion in V of this poset, then this is isomorphic to C. Okay.
Actually, no, I don't. This doesn't seem right. Because on the left side, every generic for B plus can be extended to a generic for this star thingy.
No, I mean, this is a two-step forcing. So this
Yes.
is a forcing.
So in particular, every generic for B can be extended to a generic for the two-step iteration.
Yes, you're right. Complete injective. Yes, you're right. Yes, you're right. So what happens is, let me say what happens in the specific case where I
I'm sorry,
factor.
I'm very sorry, but I'm like trying to stay on the surface. So you're saying that here
Can you
just
speak louder because I'm not hearing
okay.
well?
Yeah, just to sound this check. So here you're just restating the fact that if I have an inject, like one algebra is embedded as a complete way into another, then if I make two-step iteration, that what I get is just if I
Yes.
force with later, but this is re-expressed in the terms of Boolean algebras directly.
Yes.
This is okay. Yeah, I just wanted to.
Okay.
Right.
And in fact, the point is that if I from B to C is a complete homomorphism, well, let's say is complete, let ker I, so let me use this terminology, equal to the sup of B in B, such that I of B is equal to 0 of C, and the co-ker of I to be the negation of the ker of I. And then we have that I splits as, let's say, IB. Well, let's say, let's call it B, KB, that goes from B to B restriction B and sends R to R wedge B, and IB that goes from B restriction B to C and sends R to IR, and this is injective and complete, and this is complete and surjective. Okay, so I mean, well, I will focus on this type of homomorphism, which are not surjective, but which are not injective, but I mean, they are essentially, you split this homomorphism in two pieces, one piece, so these homomorphisms tell you that you can split your Boolean algebra in two pieces, B restriction B and B restriction not B. And on B restriction B, you get an injective complete homomorphism, and B restriction not B is, let's say, thrown out by this homomorphism. C will not remember anything about B restriction not B. It will just remember B restriction B. Okay?
Mm-hmm.
Okay, and now I can define the class
So
forcing.
just a check of, okay, so let's say I give you now generic for B, then first you see whether that generic chooses B or B or not B.
Yes, exactly.
And then if it chooses the wrong one, it cannot be extended. If it chooses the right one, then it can be
Yes,
extended. Okay.
essentially, you choose the generic for B. If it for this Boolean algebra, if it chooses this one, then this I is telling you, okay, you have got you take the pointwise image of this generic and you can use it to build the generic for C. But if you have chosen this one in your generic, then this I is saying, okay, this generic cannot be of any use if you want to build a generic for C.
I see.
Okay, and now comes the key definition. So definition, let gamma be a definable class forcing. Well, a definable class of forcings closed under two steps iteration. and we say P is less or equal gamma than Q if there exists I from rho Q to rho P gamma correct. And P is less or equal gamma star Q if P is less or equal gamma of Q as witnessed by injective gamma correct I. Okay, so this is saying, okay, if I force with P, pulling back the generic I got from P using I get a generic for Q. And furthermore, I see that my iteration, I mean, if I get that the final, well, here I have, if G is V generic for P and H equal I minus 1 G, then VH models P of gamma of C mod I G. Okay. If P is less or equal gamma of P. So this is the translation in the forcing terminology. Well, it's an if and only if. Okay. Is it fine for everybody?
Mm-hmm.
So this the point is that usually when you want to do iterated forcing, as pointed out before, you need this notion because you need injective complete embedding. You need that your Boolean algebra of interest is a complete subalgebra of the target algebra. But in order to add generics, I mean, in order to know that if you add a generic for this, you are adding a generic for this, you just need that a piece of this Boolean algebra embeds a complete as a complete subalgebra of this Boolean algebra, of the completion of this Boolean algebra. Okay, and I think that I'm almost going to stop, so we will look at the class forcing gamma less or equal star gamma. Okay, and the idea is that here in the place of gamma you can put proper, semi-proper, stationary set preserving, or essentially what you need is a iteration theorem which tells you that you can survive at limit stage, closure under 2 steps iteration, and an ingredient which is not very transparent at the moment, which is rigidity. You need the rigidity of this forcing, which I will spell out next time. So I think I stop here. But the idea is now we are going to use this forcing in the place of col omega less than ord, and more or less mimic what we did for col omega less than ord, and cook up a notion of, let's say, resurrection axiom for the theory of HLF2, which is similar to projective resurrection. Well, actually, I can state it. So let's say a definition: BCFA gamma, bounded category forcing axiom for gamma is, let's say, gamma being, well, let's do it for a SSP forcing. SSP forcing is H omega 2 is, well, let's say epsilon is fully elementary in VH if H is C generic for SSP less or equal star SSP. Okay, and
Do you mean
since this
H omega 2
forcing,
of
I
H?
mean, the idea is if you force with this class forcing, you are adding generics for all the forcing that you are putting in the generic for the class forcing.
Do you mean H omega 2 of VH or what?
Idea if
On the right hand side, you
well,
mean
yes,
H-
well, this will be H omega 2 of CH. So we are working over
okay,
models of
okay.
MK
Okay.
for C epsilon B model of MK. Idea is P belongs to H. In VH, there exists a G, be generic for P. So this VH is making true as many possible forcible statements that you can imagine to make true using a stationary set preserving forcing. But I will expand on this more next time. I'm out of time.
Okay. Thank you, Matteo.
And thanks to you for the patience.
All right, guys. See you next time. See you next week.
See you next
Yeah.
time. Bye.
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 Ciao, ciao.
Bye.